No, this is not a figment of your imagination. Your professor has not lost his mind. However, he's willing to make a fool of himself and wear Spock ears on the day of the review to emphasize the fact that I detect a lot of panic out there from talking to students. We need to start thinking logically, like Spock, like the Star Trek Vulcan, okay? And that's what we're going to do today as we review for this third exam. So hey, let's go to the board. Let's talk about what's happening. Lots of things going on this week and next. Well, first of all, at the end of this week, you'll turn in your third homework assignment, all right? November 10th, Friday. Usual thing. You have your link on Canvas. Make sure you include printouts. If you answer any questions based on statistical printouts, make sure you include those in your homework answers, all right? And as we've been saying, the stat lab, the TAs in the stat lab will move at various times to the CIS computer labs, okay? They're posted up on Canvas. I'll show you here in a second that schedule, but various times there. And if they're not in the CIS labs, they're going to be in the stat lab, okay, during their normal times. So make sure if you need help, you go there. And of course, looking ahead to next week, and why we're, today we're reviewing is because you have an exam. You have exam number 3. I'll give you more details on that in a second. That's next week on Wednesday and Thursday. But I do want to point something else out to you, okay? Because this is kind of like the only opportunity, one of the few opportunities I have to talk about it. I had promised you at the beginning of the semester that at some point you would actually have fun in this class. I know it's been torture up to this point, okay, with regression to many of you, but we're actually going to have fun, and you're going to actually also, everybody's going to have an opportunity to earn more bonus points for your final exam. So we're going to play Jeopardy. I call it Jeopardy Stat, okay, just like the game show Jeopardy on television. Instead of questions and answers, it's answers and questions. And I need contestants, though, and these contestants, you students, have to be A students. So any student that is an A student, that has an A average, 90% or better average, okay, can volunteer to play Jeopardy Stat. You would come to the studio on November 20th. That's the Monday of the week of Thanksgiving. Okay, Monday, November 20th in the CIS 1044 classroom studio at 8 a.m., okay, and to come to play the game. And if you volunteer to play and I pick you to play, then you'll earn some bonus points. If you win, you'll earn more bonus points. You'll also be playing for your section. So if somebody comes in from the Monday, Wednesday, 8 o'clock class and plays and wins, everybody in that section will win a bonus point. And plus, by watching, you can earn a bonus point. Just by watching, you can earn a bonus point. And then even more, at least one of the Jeopardy Stat questions slash answers or answers slash questions will be on the final exam. So a lot of good things will come out of that. Nice little practice for the final, plus you get to have some fun. So, but I need volunteers, so those of you that have A averages, let your TA know that you want to play, and then, or email me that you're interested in playing, and then I'll pick the top students, and then you students come in and play. So that's November 20th. All right, let's go to the board, smart board. Okay, so here's the stat lab schedule, moving to the CIS 1034, 1035 computer labs. Like I said, that's posted up on Canvas. Today, I'm actually doing this lecture on November 8th. But you see the rest of the remaining 4 time periods where they're doing that to give you some help. All right. Here's details on your third exam. Okay, so it's next week, November 15th and 16th, in-class test. Okay. So you come to your regular scheduled classroom, class time, like always. And it's going to cover Chapter 12, which is the multiple regression chapter, and basically it's really covering your project data. Everything's going to be on your project. Of course, you're going to bring your picture ID. No, won't be printed cell phones or calculators during the exam. And then make sure you bring in 13 clean statistics printouts. Clean meaning no highlighting, no writing, no marking on the printouts before, during, or after. Of course, you can put your name on there and you can number them. But other than that, keep them clean. You'll be in good shape. So that's exam number 3. Now, like I mentioned about Jeopardy Stat, here's a peek ahead at the remaining lecture schedule. It's important because we've got remember, USF has reading days the week of Thanksgiving where I can't have a class, can't make any homework due or any assignments due. We can't even open the stat lab, okay? So it's basically reading day, it's your day. So here's what's happening. All right, next week, okay, not this week, but next week, there'll be a lecture prior to the test that won't be covering anything on the exam, but of course that'll be material that's important for the final. Then you'll have your test on November 15th and 16th. That's exam number 3. Then the following week, the week of Thanksgiving, like I said, November 20th, that's the lecture on Jeopardy Stat. That's where we'll record the Jeopardy Stat game. Everybody will have a chance to win some points, okay? And then basically we shut down the whole rest of the week because of the Tuesday and the Wednesday are reading days, so no stat lab, no class, nothing there. And then Wednesday, of course, is another reading day, so no class, no lab. and then Thursday and so on to Thanksgiving. So shut down the rest of the day. So if you want to watch Jeopardy Stat and you don't come on Monday to watch it, okay, you'll have to watch it online. But that's fine. That works. That'll work. That's fine. That's no problem. Then the last week of classes, we have a lecture, we have a review for the final, and then the final exam is actually December 2nd. Okay, that's the final. I'll get more details on that the closer we get to it. So anyway, that's the remaining schedule. All right, now let's talk about reviewing for exam 3. Actually, I want to jump ahead and then come back. Okay, brief review of last lecture. Just a brief review of last lecture. All right, 2 topics we talked about. We talked about multicollinearity and we talked about stepwise regression. How are these important? Well, the multicollinearity issue is one where your x's are correlated. That's bad news. Okay, that could present problems with your results, beta estimates, having wrong signs, opposite from what theory says, t-tests on betas being non-significant when you know they're really important variables. So lots of confusion could occur if you ignore this problem of multicollinearity. So as far as your project goes, all I'm having you do is identify whether or not you have multicollinearity, whether your 2 x's are highly correlated, like a 0.7, 0.8, or 0.9 correlation coefficient. And by the way, it can be negative too, negative correlation. Somebody asked me that in the minutes papers. What if I get what if I get an R correlation of a minus 0.83? Is that okay? No, that's not, because absolute value, right? Take the absolute value of that thing, and it's pretty high. And so that would imply you have a problem. So we talked about that. And then we also talked about the use of stepwise regression, on how it's really easy to use, but it's misused a lot because researchers, users of regression, often mistake this for a model building tool, and it's not a model building tool. It's a variable screening tool, which means if you have too many x's to begin model building with, you run a stepwise regression to reduce the number of x's, and then you begin model building. So you don't just ignore model building. This is just comes right before it. So we talked about those 2 ideas. All right, now let's review for exam 3. Here's the things I want to go over. Some helpful suggestions, things that I think are going to help you prepare for the 3rd exam and do well on it. First, just to get an overview of what regression is all about. Okay, and in the text, there's a nice flow chart, a guide to multiple regression. It's on page 782. I'm going to flip over to it right now. Okay, and show it to you in the overhead camera. And there it is. Okay, so how does this work? Well, whenever you're doing a regression, the first thing you're going to do is figure out what your independent variables are. You've got to decide on your independent variables. So how many do you have is the first question here. If you don't have too many, like on your project, you only have 2, right? I limited you to 2 on purpose. Okay, but if you only had 2 or 3 or something like that, few in number, you would go right on the flow chart. If you have numerous, like a lot, like maybe 10 or more, this is where you would run the stepwise regression. And notice that's way at the top of the flow chart here. And you don't stop after running it. Okay, you run it, you reduce the number of x's, get it down to a couple, like on your project, and then you kind of meet up with what the other branch. All right, so now you're few in number in the terms of number of x's. Now you start hypothesizing models involving those x's, like you're doing for your project. Okay, I gave you 4 models that you had to look at. We're going to go over those again today. So anyway, these models have interactions, higher order terms, squared terms, things like that. All right, so you have these models. You figure out what your best model is. You test the models. You evaluate the models. Somehow, one of these models is going to be the best one. All right, but you don't stop there either. Now you conduct a residual analysis. That is, you check the assumptions. All right, make sure that they're all reasonably satisfied. That's what you're doing for the project. If there's some potential violation, all right, you make model modifications. I'm not having you do this step, okay? Many of you I know have problems with your assumptions. I've talked to you already. Okay, but I'm not having you do anything. Just tell me about it. Tell me what you would do. Okay? But in real life, you make the model modifications, like making a variance stabilizing transformation, something like removing outliers, something like that. Anyway, once you do all that, now you're back to your best model, readjusted, and of course you evaluate it, do the global F-test, evaluate R-squared adjusted, evaluate twice the standard deviation, and then in real life, of course, you would decide whether or not this model should be used for inference making purposes. I'm having you all do the inferences anyway. Your model might be a lousy model, but I'm still having you go ahead with it. But in real life, you might stop. But so here, if the model is adequate, you're going to use it for estimation prediction. I'm having everybody do this, irregardless of whether or not your model is deemed adequate. But if it's not adequate, you'd start over again. Back to the drawing board. See the arrow go back up? Oh, you don't see that. See the arrow come back up to hypothesizing other models. Okay, so that's really the big picture. That's what regression is all about. Okay, and so that's a much different view than what it was when we first looked at simple linear regression. Okay, all right, so that's that. So that I hopefully will help you. All right. Now, another thing that I think would be wise to do for practicing for this exam. I know you're really concentrating on your data, your project, and you should, okay? Because I'm going to be asking you questions about your data and your project. But if you really want to test yourself, if you really want to know whether you understand this stuff, because let's face it, you can come into the TAs or me, and you can ask us lots of questions, and we'll tell you the answers, okay? And a lot of you will memorize that, and you know, as long as I ask it in the same way on the exam, you'll know exactly what to write down, and you'll get credit for it. But what not always, but many times have no idea why you got it right, okay? So one way you could rectify this is to try other data sets. And I picked out 3 in the textbook. The reason why I picked out these 3 is because they all are like your project, okay? These are exercise 12.95, 12.161, 12.168, because they all have 3 variables, a quantitative y, a quantitative x1, and a qualitative x2 at 2 level, just like your project. So you could go in, create all your variables. The data sets are there. Create all your variables, do all your printouts, practice. So that's one way to do it. Now, I know many of you struggle with practical interpretations. I've talked to a lot of you in my office, okay? And many of you get tripped up on those. Well, to practice on that, look at the class notes. All these practical interpretations are bolded. They're easy to pick out. They're easy to find, so you can practice on those by looking at the class notes. What else? Well, that green handout, the one that describes the project, okay, the green cover page. All right, there's a flow chart on there. There's models on there. It tells you how to test the models. The flow chart explains how to test the models. Let me just show that to you. I'm going to put it up on the overhead here. Okay, and turn to it. All right. Whoops. There we go. All right, so there's 4 models. I'm talking about the bottom of the flow chart, or bottom of the page, first page. There's your 4 models, okay? This is where we're using our Spock logic. This is where we're thinking like Vulcans, okay? Very extremely logical. I'm having you figure out which one of these 4 models is your best model. We'll come back and show you those models graphically in a second, okay? But you can see the first model has curvature and interaction. The second one just has the interaction but no curvature. The third one has the curvature but no interaction. And the fourth one has neither the curvature nor the interaction. So the first test I want everybody to do is the test for curvature. Okay? That means you compare model number 1 to model number 2. And somebody said, why? You're telling me that. Okay, I'm going to accept that and I'll do it. But why? Well, because think logically. If I want to know whether curvature is important, I try a model with curvature in it. That's model number 1. And then I try a model with the curvature removed. That's model 2. That is why we're comparing model number 1 to model number 2, because one has curvature and one doesn't. So we want to know which one does a better job. All right, so we conduct that test. That's a partial F test. I don't put the null hypothesis here, but I wrote it up for you now. The null hypothesis is these 2 betas, beta 2 and beta 5 equal to 0. Now, why am I picking these 2 betas? Logic tells you, look at the models, the 2 models. What's the difference between the 2 models? What are the 2 betas in model number 1 that are not in model number 2? Oh, beta 2, that's a squared term, and beta 5, that's a squared term. That's why. That's why we pick out those 2 betas to test, because we want to know whether we really need them, whether we really need the curvature. So you conduct that test. That's a test for curvature. We'll have more details on that when we do the sample test. All right, you'll get a p-value, you get a printout, you get a p-value. P-value tell you which way to go. All right, if you reject the null hypothesis, you go left on the flow chart. That means keep curvature. Reject HO means keep curvature, because you're rejecting this null hypothesis of no curvature. So therefore, you're going to keep it. If you go right on the flow chart, it's because you failed to reject HO. So what do you do with curvature? Well, logic says if it's not important, drop it. Take it out of the model. And that's exactly what we do. So right means remove it. Now you're down to model number 2. Left means keep it, the curvature I'm talking about. And now you stick with model number 1. Now, no matter which way you go, the next test you do is a test for interaction. It's the same logic. How are you going to test for interaction? You try a model with interaction in, then you remove the interaction and try a model with the interaction out, and you compare those two models. And it turns out that over here on the left, it's comparing 1 to 3. And look at 1, look at 3. You can see the difference. The difference between the two models is the two interaction terms, beta 4 and beta 5, and that's why I'm testing the null hypothesis that beta 4 and beta 5 is 0. If you want right on the flow chart, you're comparing model number 2 to model number 4. Why those two models? Well, first of all, they don't have curvature, and that's why because we're going right in the flow chart. But looking at the two models, you can see that model 2 has interaction, model 4 doesn't. That's exactly what we want. So you do that test. Anyway, p-values come out. Same logic. If the p-value is small, you keep the terms you're testing, so that's a rejection of the HO. So over here, if the p-value is small, I keep interaction, and I kept curvature from the first test. Now I keep interaction on the second test. That leads me to model number 1. And you say, well, why is model number 1 the best model? Well, think about it. What did we just do? We just showed that we needed curvature. Then we showed we needed interaction. What's the only model that has both curvature and interaction? Model 1. Same logic here. Why is model 3 best here? Because I kept the curvature from the first test. I dropped the interaction from the second because of the second test. That leads me to model number 3. Likewise over here, drop curvature first test, go left in the flow chart here, keep interaction on the second test. What's the model that has no curvature but has interaction? Look at it, it's model 2. And then likewise, first test, no curvature. Second test, no interaction. Drop both out. What are you left with? Model 4. So all this is extremely logical, okay? Extremely logical. That's why we're thinking like Spock today. All right, so that's that. Now we're going to come back. Well, actually, let's do this. Let's look at now the 13 printouts, okay? The 13 printouts that you are bringing in with you to the exam. I'm going to put one thing up on the overhead. The rest I'm going to show you on the sample printouts. So let's go back to the overhead camera here, because I want to make sure, whoops, that you do not turn in this printout. You're not bringing this one with you. Okay? You're not bringing that one with you. That's one you did for the bonus points. I get it. Okay? But that was to help us guide you in the right direction. Now everything's in your head, and you're all on your own here now with your data. You should know this by heart. You really should know this stuff by heart. So don't bring that one in. Don't bring that one in. Now, as far as the other printouts that you're bringing in, let's take a look. Okay, these are all posted for you on Canvas. All right, first one, and remember now you can label the printouts the same way I've labeled them, but no more than this. Okay, printout number 1 is just simply your data listing. Okay. When we actually get to the sample test, we'll come back and look at each one of these and figure out, how they help us. Printout number 2 is a scatter plot of your actual data. All right, actual data there. Printout number 3 is the correlation matrix. Of course, this is the one you check for multicollinearity, just on whether or not your x's are correlated. Printout number 4 is your model number 1. Everybody's going to get a printout for model number 1, just to make sure you can actually estimate all the betas you need to estimate. Printout number 5 is a subset F test to compare model number 1 to model number 2. This is that first part of the flow chart, trying to figure out whether you have any curvature. Of course, you're going to look at the last p-value. That's going to tell you. Turns out I don't need it. You might. Printout number 6 could look like this, comparing model number 2 to model number 4. It could look like the one above, comparing model number 1 to model number 3. It all depends on whether you kept the curvature. Anyway, you find the p-value for interaction, determine whether you need it. Okay, determine whether you need it. Some do, some don't. Anyway, you end up with your best model like I just showed you. That's printout 7, whatever your best model is. May not be the one I'm putting here. Okay, but your best model is number 7, or printout number 7 is your best model. My best model is number 2, but printout number 7 shows that. And of course, we would evaluate the goodness of the model right here. Printout number 8 is confidence intervals, prediction intervals. Remember, you have to select values of x's that make sense, and the ones that are in your model, these are down here. So we know how to interpret those. Then we save some residuals and we save the predicted values. And then we get printout number 9, which is a list of all the standardized residuals. This helps us detect outliers, Y outliers, and Y suspect outliers. Remember, a Y outlier, or standardized residual greater than 3 in absolute value. A Y suspect outlier, standardized residuals between 2 and 3, in absolute value, of course. That's that list. Printout number 10, scatter plotted residuals versus the quantitative X. This helps you check the first assumption about the mean error being equal to 0. Checking for a misspecified model. Hopefully you won't see any kind of curvature here because that would be bad news. You'd have to go back and fix your best model. Printout number 11, scatter plotted residuals versus the predicted Y. This is checking the second assumption. That assumption is about constant variance. Hopefully you don't see any cone shape here. But if you do, just tell me about it, that you would make a variance stabilizing transformation. Printout number 12 is a graph of your best model. I'm going to go over those here in a second of all the models, but this is what my best model looks like. You should get perfect straight lines and curves here. If you don't, you didn't do this correctly. Okay, so it should be perfect straight lines and curves. And then finally, the last printout, number 13, is a stem and leaf plot of the residuals to help you determine if you're satisfying reasonably the assumption of normality. This also helps for outliers too. So those are the 13 printouts. You're bringing those in with you and not marking them up at all. Okay, let's go back to our list. So I want to go back to the models. All right, because I know got a lot of questions from students in minute papers that wanted me to do this again. They want to know, how do I know what my best model should look like, the graph of my best model? How am I going to know? How am I going to know? Well, let's go back to the PowerPoint where I actually showed this. This was actually lecture 16, and just easier if I just go back to it. Here's model number 1. And you can see that what is inside of model number 1. What kinds of terms are in model number 1? Well, there's curvature terms and there's interaction. We talked about that. So now how are you going to graph it? How should the graph look? You could play around with the betas like I did there and put them all together in the right way, and you're going to get your answer. But there's a much easier way, a very logical way to figure out what this graph's going to look like. Okay? And that's the approach we're going to take. Well, okay, we've got curvature in the model. That's obvious. There's squared terms in there. So we know we're going to have curves, not lines. Okay? You have to have curves. Now, how many curves? Well, how many levels of the qualitative variable? Of course, my case it's gender, male or female. Yours could be that. Yours could be something else. But it's 2 levels no matter what. So that means 2 curves. And then how should the 2 curves relate to each other? Well, notice there's interaction in the model also. Interaction means the curves should look different. They're not going to look parallel. They're going to be non-parallel. So 2 curves, non-parallel. Your graph, if your model number 1 is your best model, and you get down to printout number 12, I guess it is, and you don't see a graph that looks something like this where you have 2 curves non-parallel, then you made a mistake somewhere and you have to go back and fix it. That's what your graph should look like. If it's model number 1, 2 non-parallel curves. All right, model number 2. Again, you could play around with the betas, substitute in the zeros and ones, and you could figure out what the line should look like. But we're going to do it logically. All right, so we look at the model. We see what's in the model. Doesn't have any curvature in it. No more curvature. No squared terms. But it does have interaction. Okay, the fact that there's no curvature means I'm going to have lines now, right? Straight lines. How many? 2 again. Why 2? Oh, qualitative variable, 2 levels, 0, 1. And why am I showing the 2 lines non-parallel? See, we're playing Jeopardy right now. I'm giving you the answer. 2 lines non-parallel. And you're coming back and telling me what is interaction. I have interaction in the model. Interaction causes the 2 lines to be non-parallel. See, logic gives you the result. Of course, you know that's what my graph looked like. I guess I did mine right. I'm good. Let's go to model number 3. How is this going to graph out? Well, look at your model. Look what's in it. Has some curvature. Does not have the interaction. Okay, curvature means curves. Dummy variable, qualitative variable in the model means 2 levels, so 2 curves. And no interaction means the 2 curves should look the same, parallel. 2 parallel curves. 2 parallel curves. That's why.